we have Diana Borsa with us. Thank you so much, Diana, for joining us. So Diana is a research scientist in DeepMind, and I will let her actually to tell us a bit more about her background before she presents the talk. Thank you, Diana.
Thank you, Viorica. As she said, I'm Diana. I'm a research scientist in one of the core RL teams in DeepMind. I've been at DeepMind for a bit over 3 years now, and before that, I did my PhD in University College London and Microsoft Research in Cambridge. I am a mathematician at heart and by birth. I started machine learning in Bayesian statistics and variational inference, but in 2014, I stumbled upon this exciting problem called reinforcement learning and pretty much never looked back. Okay, so hopefully I can get you excited about this problem as well, and we can do this journey together. Okay, let's begin. First, I would have to do a disclaimer that this starts from the very beginnings of reinforcement learning. I do not assume any knowledge about this field, and we're gonna build up towards the formalization of the problem, the core concepts here, all the way to how to pair this with functional approximator techniques or deep learning techniques in order to scale up these problems to the successes that they have had recently. So this, for people who do have some knowledge in RL, you can maybe skip forward, but it's always good to have a different take on the problem by someone. Okay, so to begin with, let's start with what is RL and why should you care? So today we're gonna define reinforcement learning as the problem of sequential decision making that can have long-term consequences. It doesn't need to, but typical problems do have this property, and potentially very sparse feedback. Again, it's not necessarily that this is the case, but the most challenging and problematic problems will have this property. Going a bit more into what this sequential decision-making problem often entails is actively reasoning and trading off short and long-term consequences of your actions and the payoff. This is just an example. This is, sorry. A representation of a scenario like that, where short-term consequences, like going into any of these corridors, the first thing that you would see, you get a negative reward every in any of these paths. Now, of course, there's you can see that there's a path here where that would lead to a positive reward down the line, but you have to trade off the negative reward that you get in these intermediate steps in order to get to the high reward at the end. So this is very typical of the reinforcement learning problems and sequential decision making problems. To complicate things further, usually we assume in reinforcement learning that the conditions of the world are unknown. That means the world and the environment that we are interacting it is unknown. The reward structure can be unknown, and the feedback is often sparse, delayed, and unknown, which means that we have to reason actively about how to gather information about the world, how to explore in this world in order to discover the structure of the world. Some examples of decision-making problems that we can model in this framework are flying a helicopter, planning a trip, maybe optimizing for time, optimizing for cost, optimizing for minimizing the delay, or controlling the efficiency of a power plant, controlling the relevance or the experience interaction for web searches, movie recommendations, TV recommendations, product recommendations, managing a portfolio, playing chess, playing video games, and so on and so forth. So this is usually this is a very big class of problems that we can handle in this framework. There's maybe a couple of more examples that I want to highlight that are not usually thought of as reinforcement learning problems. One is the one-time decision problems under uncertainty. These are usually called bandits. And although they do not have the sequential nature, they do have the exploration component in there, because we have to reason about identifying the best decision under uncertainty and trading off how much we're exploring each action to identify the best one versus the payoff that we would get at the end. And even something like classification problems can be recasted in this formulation, but again, it's a very limited formulation in the sense that it's a one-step decision. The action is the class of that classification or the label of that classification, and the feedback is immediate, because you get to see if you done it right or wrong, or there's a loss associated with that. This is usually not the case in reinforcement learning problems. You get the very sparse feedback at the end of a sequence of actions that part of the problem is doing the credit assignment, trying to understand which of the actions were actually relevant for the outcome that you got. Now, all of these are reinforcement learning problems, and I want to highlight that RL is not a solution, is the problem, is the paradigm of thinking about decision making and their consequences. Okay, now we're gonna jump into some of the fundamental concepts of reinforcement learning and how we're gonna translate this problem into a mathematical framework. And to begin with, the usual reinforcement learning system is depicted as the interaction between an agent and the world. The interaction is usually done by agent sending actions to the world transitions to a new state, it gets an observation back and a feedback signal, potentially sparse feedback signal. So more formally, mathematically, we will model this interaction by a Markov decision process. And Markov decision process is just a tuple that includes the state space of the agent, which states are feasible, which board configurations in a chessboard are feasible, the action space, which actions are available to the agent at any point in time, as well as the interaction, this interaction, temporal interaction, which means at each point in time, the agent resides at time t in state t and takes an action at. Then it transitions to state st+1 according to this probability kernel, which is considered in most of the RL problems stationary, as well as given feedback from the system, which is a function of the state and action that was taken. Optionally, in the problem specification, we can have a discount factor that basically says how much more useful or valuable a reward at this point in time is with respect to something that I would get in the future. Okay, and this process now unfolds in time over multiple time steps, and the assumption that we're making to make this problem tractable is the Markov assumption, which says that the future is independent of the past given the present, which means in this diagram that if I'm at this state, anything that has happened before that is irrelevant to my predictions in the future. It's not that I can predict the future perfectly, it's that no information from the past can add to my ability to predict the future or my way of acting. So everything is contained in terms of history in that state. Okay. This happens to be quite a rigid assumption. At the same time, a lot of the algorithms that we're gonna look at actually work outside that assumption. It's just the mathematically we can investigate things more in this framework, and a lot of our algorithms will heavily exploit this Markov assumption. You can see the others as just an approximation to this paradigm. Okay. The other assumption that we're making is maybe it's not an assumption, it's a hypothesis, is the reward hypothesis, which means that any goal can be formalized as the outcome of maximizes of cumulative reward. And the rewards in our setting will always be scalar feedback signals that are a function of the state and action that we're in right now. And the goal of an RL agent is to find a policy that maximizes this expected cumulative reward. Okay. Moving on, there's the notion of cumulative reward can be has a couple of different ways of formalizing this. The most popular definition there is the discounted infinite horizon, where we sum the rewards that the agent will obtain during its lifetime and discount them according to their place in time. And this is for continual learning problems, because this is an infinite horizon problem. This is by far the most common formulation, but of course, if your environment is not infinite, you can do this with an episodic setting or a finite time horizon, which is the second formulation, where basically is the same sum discounted, but we are only going to take into consideration that sum to a time t where the episode terminates or the environment times out. And the last formulation that is quite prevalent still is the average reward, which is kind of making a comeback in the continual and lifelong learning scenarios. But for most of the papers and RL problems out there, both the theory and the algorithms are derived in the discounted infinite horizon framework. So we're going to focus on that for the purpose of this talk. And just note that all of these variables are actually random variables. They are sampled given your state and action. So the whole thing here, like this return, is a random variable as a function of the trajectory that has been executed in the environment. So in order to get the policy out of it, we want behavior that on average gets the best return. And this is basically formalized by value functions. We have two of them. One depends only on the state, and the other one depends on the state and action. And these are exactly this, is the expectation of the return given that I started in state S, and the action value function says I started in state S, I took an action A, and what is my expected return over all the trajectories in the future that I will be taken after that. Okay. Now, because of the Markov property, the value function have this nice recurrent relationship where we can break up this equation into two parts: the immediate reward And what remains in the sum can be reinterpreted by the same definition as the value function of the next transition. So I started in in state S. I took an action A, and then I have multiple futures available to me. Transition to according to the probability of transitioning to another ST plus 1, and taking an action after that, multiple actions after that. So all I'm saying here is that I'm gonna break this equation into the value at this state, and this action would be the reward I got during this transition, and the expectation over the state and action at the next state. Okay. And this leads us to exactly the Bellman expectation equation. And this is one of the most fundamental equations in RL. So if you're going to retain anything from the stock or memorize anything from the stock, please let it be this equation. This is at the core of all the algorithms that we do out there, both for control and for prediction. And I guess, why is this so important? I think that the key here is exactly this recurrent nature of the relationship, where basically this allows us to bypass looking at the whole trajectory and taking the expectation over the whole trajectory to compute this value function, and we can only look at the neighborhood around that function at the one-step transition. Okay. Let's try to make this more formal, and looking at the computation of a value function and the credits assignment problem. So this is just one trajectory, but usually when you do this computation of the value function, you have to take into consideration all of the possible scenarios that could have happened once you're in a state and taking many actions in that state. So this happens to be now a terminal state. So I would have to back up in the value function here all of the possible futures that could have happened when the episode terminated. Okay. At the same time, at the next step, I would have had to do the same. I have multiple possibilities there of continuing. But because this is not a terminal episode anymore, usually I would have to look at all the trajectories that would have ended in a terminal state, which means all of these trajectories that might have happened. Now, the Bellman equation basically says that I don't have to do that. I don't have to go all the way and unfold this to the end of the episode. I can only look at the neighborhood and use the value functions, which are already expectations at that point, that summarize all the interaction that could have happened after that. And this saves a lot of computation and reuses very efficiently a lot of the individual solutions that these value functions contain. Okay. Okay. Now that we have the formalism, we've seen what the Markov decision processes are, what our assumptions are, and formalized our goal of optimizing the cumulative reward. Let's look at a couple of classes of problems that you usually have in RL, and I've structured them in 3 major classes here. The first one is prediction, the second one is policy improvement, and the third one that we're going to build up to is control. And we're going to start with prediction. And prediction can be anything useful in the environment that will inform your actions. But for our purposes, we're going to look at a particular prediction problem, which is policy evaluation. And policy evaluation basically wants to answer a question, the following question: given a policy, what is my expected return under this policy? If I were to go into the environment and execute this policy, what am I expected to get if I do this? And in order to answer this question, probably the most trivial or naive solution that you can think of is, well, you just sample trajectories in the environment, see what the return is on those trajectories, and just do a sample average to get an estimation of the return. So we start at one point, we act in the environment according to this policy, and all of these provide me with a sample version of the return, GT, and I'm just going to do a mean over these things. So this is very like a very natural solution. Unfortunately, this tends to have high variance and be quite sample inefficient. Like in the picture that I just drew, you can see that even if I start in S1 and unfold a lot of trajectories starting from S1, unless these trajectories overlap partially or intersect, for all of the individual points in these trajectories, I might have only one sample to get the return, to get an estimate for the value function of that return. So for all of the individual points here, I only have one sample corresponding to this return. Now the question becomes, given our assumption, can we do better? And this is exactly what we're gonna do by using this Bellman equation. And there's two strains of work that kind of mirror each other. One is dynamic programming, and the other one is temporal difference learning. The only difference between them is in the first one, we assume that we can, in principle, evaluate this expectation exactly. So we can back up the Bellman equation exactly. In this usually is not the case because we don't have access to the environment or to that transition kernel. So the most prominent one is still temporal difference learning, where the concept is exactly the same, but instead of having the exact expectation, we're going to just have sampled versions of this expectation, and we're going to try to approximate this expectation via samples. Okay, so we're going to go through the principle of dynamic programming because the convergent results and things like that are more well understood here, and then we will extend this to the sample version. Okay, the idea behind the dynamic programming is turning this equation, the Bellman expectation equation, into an update. So instead of that being inequality, this is now an update, and this is exactly what this equation says. I'm just rewriting things in terms of an operator. Now, it turns out that this operator that we defined here happens to be at contraction, which means that if I sequentially apply this operator, I will get a sequence, a convergence sequence that that will converge to a unique fixed point. The fixed point of this operator, which by construction has happens to be the value function that we are looking for. You can easily verify that the equation of the fixed point is something like this, or in operator form, this, and the function that satisfies the fixed point equation is exactly the value function corresponding to the policy that we're trying to evaluate. Okay, so this basically says if you start anywhere in the space of bounded value functions, applying this operator over and over again will eventually lead you to the fixed point, which is exactly the value function that you're looking for. Okay. Now, temporal difference methods basically say, like, I don't have access to this update, but I have access to just samples from that, and I will try to approximate this update by not exactly backing up toward exactly that update, but towards this update. This is the sample version of this expectation. And we're going to move the values of our Q function towards this target. This is usually called the TD target. And the whole term there is usually referred to as the TD error. The term comes from the fact that this is usually seen as an online algorithm where you are in state S, you take action A, you transition to ST plus 1, you take another action ST plus 1, and based on that transition, this is the correction that this new evidence will give you. So based on this new transition, is your value function, is your current estimate of the value function coherent or consistent with this transition? If that would be the case, if you would have the right value function, then the TD error here would be 0. If not, this new transition will give you some more information. Okay. And this particular update is used everywhere, and it has a very general form. We can also think of all the methods that we described before as in terms of this update, where now the TD target can be, for dynamic programming, is the entire expectation. For Monte-Carlo returns will be only the sampled return. This is to the end of the trajectory. And for one step, which we've seen before, TD learning is just the one step sampled version of this update. Okay. A different way of looking at it is, or of visualizing it, is that we have sampled methods and full backup methods. And temporal difference learning basically looks at only one update in that, like 2 sequential states, so only has to look at the neighborhood. Monte-Carlo will like unfold this to the end of the episode and do this exhaustively. Dynamic programming will also only look at the neighborhood. So this is this equation. It only looks at the next transition, but it looks at all the possibilities of the next transition, all the states in action that could have happened after that, rather than the sampled version here. And at the end of the spectrum, where you would do something like Monte-Carlo of like running your system to the end of the environment and looking at all of the possibilities, would be something like exhaustive search. And we just don't want to be here. This is for most of our environments, this is not feasible to even represent. So we will be exploring this quadrant. Okay. Another view on it is this updates. If you do have the MDP, go ahead and do dynamic programming. This is probably the best trade-off that you can get. If you don't have access to this MDP, then a sample version of this is Monte-Carlo, and the sample version with bootstrapping, so relying on your estimate to do your update, would be something like an n-step return. Okay. Now you might think how these two sides of the spectrum relate to each other, and as I hinted before, this happens to be a bias variance trade-off, in the sense provides us with an unbiased estimate of the value function that we're trying to compute. This is just the ID samples. On the other hand, the TD target, at least the one-step TD target, is usually a bias estimate, unless your value function at the next state is already the value function that you're looking for, which is for most of the learning that won't be the case. At the same time, TD has a lot less variance, just because it looks again at the neighborhood. It looks at only the stochasticity in the next transition, rather than something like Monte-Carlo, which unfolds over time, over multiple steps, and has to integrate over that uncertainty. Okay. And of course, like the question becomes, can we do something in between? And of course, there are two extremes here: the one-step return, but we can do things in between. So here I'm just showing the two-step return, where we're unfolding the environment in for 2 steps and then bootstrapping. In general, we can do that with an n-step return. And as n tends to infinity, we recover the Monte-Carlo return. So this will automatically trade off this bias and variance introduced by the bootstrapping and the variance, the high variance that Monte-Carlo return has. Note that, like this, at least for the discounted return, this trade-off is very natural, because we are relying on actual experience, and you're not bootstrapping on your value. As n increases, then this factor here tends to 0. So you are naturally relying on the bootstrap value less and less as n continues, as n progresses to infinity. So there's a spectrum there between how much bias you're introducing via this bootstrap, and how much variance you're introducing by the n steps that you are recording in the sample. This is just an empirical evaluation of this insight, where we just have a scenario where we update we use this update to compute value function with different n-step targets, and we can see that for instance, for this problem, n equals 4 seems to be the best one, but this tends to be very, I guess, problem dependent and policy dependent and so on. So this is pretty much a tunable parameter, but it does give us basically a knob to search over this bias variance trade-off. Okay. The last thing I want to mention here is that a different way of combining and walking that space in the bias variance trade-off is something like the lambda returns, or for that matter, any combinations of these n returns. So instead of choosing one n that might be good for all of the states that we have, you might want to let multiple of these returns vote in computing a target, and this is what the lambda return actually does. It weights the individual n-step returns with a discount, with a decaying rate gamma. This tends to be between 0 and 1, so it's always decaying. One thing to notice that is not on the slide is when computing these n-step returns, we usually have to wait till the nth step to back up these values, because we are relying on an instantiation of a sampled instantiation of that trajectory. So as the n increases, you might need to wait quite a lot to make an update. That's one of the reason we like bootstrapping, because as opposed to Monte-Carlo, where you have to wait till the end of the episode, you can do these updates incrementally. The nice thing about the Lambda return is that even though it's mixing between returns that go up to n equals infinity, there's a backward view for this equation that results in an update that is online, that you don't have to wait till the end of the episode. And the relevant piece of work there is the work on eligibility traces, where you basically store the credit assignment problem in order to reproduce something that will give that will fake basically this update, but in an online fashion. Okay. Sorry. Okay, that was policy evaluation. The second problem that we're going to touch very quickly is policy improvement, and this is the problem of given a policy or given a trajectory in the environment, can I do better? Can I improve over that policy? And this is just an example saying that maybe this portion of the trajectory was irrelevant with respect to my cumulative reward, and I could have gone to the same place in a shorter path, which in the discounting setting gives me a better cumulative reward. And the one instance of policy improvement that we're going to cover today is greedy policy improvement, which basically says, given a value function, evaluating a policy pi, we're going to construct a greedy policy by just taking the max over all the actions for that value function. This is just basically, as the name suggests, this is greedy with respect to every state. And this turned out to give us a policy that is an improvement, guaranteed improvement over the original policy pi that we started with, that we evaluated here. Moreover, this happens to be a strict improvement unless the original policy, this one that we're trying to improve on, is already optimal. Okay. One other thing to notice is that in general, policies are not necessarily ordered or globally ordered. This equation holds for all states in action. So the policy that we're getting out of this procedure, this very simple procedure, is guaranteed to dominate the previous policy for every state in action in the space. Okay, cool. Okay, before we move to control, I think I'm going to break to take some questions, because the two other problems will become relevant in this section.
Quickly share the screen so you can also see the questions.
Sure.
Okay, so you can see it. I'm assuming that the first question arrived before you got to present all the differences between RL and dynamic programming. But if you want to go like very briefly, again, just to summarize into
Sure.
2 words.
RL is a problem. Dynamic programming is a solution if you have if you know the MDP.
Nice. Why is there a sudden huge interest in RL theory over the past year or so?
I don't think it's a sudden interest. I think it has dropped actually with respect to previous years. But yeah, I think because the state-of-the-art methods right now do lack some like theoretical justification. You will see that the base algorithms haven't changed in terms of RL. It's TD learning all the way. It's most of the advances have been in trying to make this play well with functional approximator. Definitely, we haven't pushed that much on that side, unfortunately.
Okay. Why would it make sense to perform classification with RL instead of supervised learning?
It wouldn't. It's highlighting that the problem is very general. Again, it's a problem specification. It's not a solution. It's just casting multiple of these problems, including the bandit or something like supervised learning, into this framework.
Is there an alternative paradigm other than RL when thinking about sequential decision making, or an alternative to MDP formulation?
For sequential decision making, I think this is the most prominent, or the one that I have encountered more prominently. To the MDP formulations, yes, especially in things that violate this assumption, like partial observable Markov decision processes, or something related to games or multiplayer, where these assumptions, at least in terms of the stationarity of the kernel, are violated. At the same time, again, these algorithms tend to work outside the formulation, although we can't really say anything about them theoretically. That's why we like the MDP formulation. If someone can, find a better or more broad class of problems where these things have the same properties, that would be awesome.
Okay. Can we relax the Markov assumption to maybe more than one state behind, like an optimal choice of previous states, maybe some attention over previous states?
Sure. So the Markov assumption is really only saying that there exists a state that is Markov, and the trivial way of doing this is to include all the history. This will always be Markov. It's just not necessarily a very useful representation, but you can include all the history that you think it's available or relevant for the decision making, and make the states Markov.
Does the Markov assumption for RL makes it not applicable for time series where there's a certain inherent periodicity, or is RL just not a good tool for that?
Again, like based on the last comment, you can always make a state a representation of Markov. It's I guess the distinction there that I haven't made is between observation and state. What you're getting out of the environment and what you get to observe at this point might be partial, but the state has to include multiple of these in order to be a Markov state, in order to have that property that you contain all the information that you need for the future.
Maybe we take one or two more and then we move to the second part. How to deal with the environment being non-stationary?
Still an open problem. Technically, a lot of the methods out there do this already. Inheritively, in the way we're training these systems, there's non-stationarity coming from the policy anyhow, and from the functional approximator, and not being able to represent the environment properly. So again, empirically, we have been shown to be able to deal with the non-stationarity. I think the more proper way of dealing with it is to characterize that non-stationarity, and see which of the parts of the environment change, which of the variables in our state space are influenced, and maybe try to have an algorithm that looks at that and exploits what stays the same and what is non-stationary.
Okay, so the last one: why is the whole field of RL centered around Bellman equation? And if yes, why are there so many different techniques and names?
Value-based methods do center around Bellman equations. just because this is just a formulation that that allows us to cache in these solutions and have this this form of dynamic programming that is very, very efficient. Like if you were to unfold this tree and try to do the backups like that, like exhaustive search will never be able to tackle these problems. So it's just a very efficient way of doing this, and they are very flexible in that sense. Like the end step, any kind of yeah, a backup there in terms of exploitation or maximization can be done like that. This is not to say that there are other techniques out there like direct policy optimization that do not necessarily go through this route, but in order, every time we want to compute the value function, these like this is just a trick to basically make that computation more efficient.
Okay, so I think, yeah, we could move on to the next segment. So I will stop presenting now. If you could resume your presentation so that everyone can see your slides well.
Can you see them? I can see them.
So you need to go in the bottom right, and there should be a resume presentation there.
I haven't stopped presenting. I can see my presentation.
Right, but I think you need to resume such that the layout, or if you just do go present again, if you have at the bottom right, just present again. Yes, that is perfect.
Okay, that works. Okay, cool. So now we're going to move into control, which is probably the thing that RL is most associated with, which tries to answer the question how to act optimally in an environment in order to maximize this cumulative reward. And this tackles problems like optimal pathfinding, optimal strategy in Go or chess, minimizing the energy consumption in a cooling center or a power plant, trying to estimate the best treatment protocol to minimize relapse or maximize success, or anything like policies to coordinate traffic lights in a city to reduce congestion, carbon emission, and so on and so forth. So. And as I mentioned, actually in the questions, there are two main ways of tackling control: value-based methods and policy optimization methods. And we're going to only focus on value-based methods for the time being, but Doina will cover some of the more policy optimization methods where you parameterize directly a policy and try to improve that. Now, to mention that even for these kind of problems outside the basically something like reinforce or something evolutionary based, all of these algorithms will try to build or will have to build a value function associated with this just to evaluate how good the policy is. As opposed to something like supervised learning, we never have this feedback signal. We don't have a way of evaluating how good your solution, readily evaluate how good your solution is. This is the first problem that we've looked at, which is policy evaluation. So it's a problem of its own. Okay. So control is about finding the optimal policy or the optimal value function. These are equivalent just because if you do have the optimal value function, you can produce an optimal policy by just acting greedily with respect to this value. And this falls naturally from the previous greedy improvement step, where if we do improve, if we do have a value, if you do have the optimal value function, if we were to get a greedy policy with respect to that greedy policy is should be an improvement over this value function, but we know we can't improve by the definition of the optimal value function. We cannot improve over the optimal value function. So the greedy policy that we get out of the optimal value function is actually an optimal policy that will have the same value as the optimal value function. Okay, and then this is a general framework of thinking about control, and I guess by far the most general principle in terms of tackling the control problem, which is policy iteration, general policy iteration, which alternates between two steps. One is, given a current policy, we're going to evaluate this current policy. So we're gonna try to approximate the value function corresponding to this policy. And then the second step is policy improvement. We're going to try, based on potentially this estimate, to improve our policy. And this will usually be something like greedy improvement. So this is exactly the two problems that we've looked before: policy evaluation and policy improvement. So this is a general recipe of how to do this, how to tackle control. The nice thing about this is alternating between these two steps, we always are guaranteed to improve our policy. The evaluation is only used to empower the improvement step, and this by the greedy improvement theorem, this always improves our policy, and in finite settings, this will converge to the optimal value function. Now we've seen these problems before, both the policy evaluation and the policy improvement. For most of these, policy improvement will always be greedy or epsilon greedy, and of course we can have like particular cases of this general principle in terms of the evaluation methods that we've seen before. And the first one is something like Monte-Carlo control, where this evaluation step is based on a Monte-Carlo evaluation method that we've seen before. This is just generating trajectories and taking the mean. And of course, we've already talked that we can do this evaluation a lot more efficiently and maybe with less variance by using or tackling this step of policy evaluation with something like a TD method. That can be like one step, n step, lambda returns, and so on and so forth, and the improvement step stays the same. Okay. Now this is all well and good. The problem is this step in terms of policy evaluation happens to be quite expensive. As we've seen before, it's a problem in itself, and it's an iterative procedure in itself, which means that one of the steps of this iterative procedure of alternating between steps is an iterative procedure, and an iterative procedure in an iterative procedure is not the best thing to have. So the idea, I guess, here is to try to shortcut this, and instead of computing all the way the evaluation of the current policy, we're gonna just look at one iteration of policy evaluation and then try to improve on that policy, and so on and so forth. So instead of having this iterative procedure, we're just gonna look at one step of this iterative procedure and try to improve on that, and so on and so forth. Okay. How does this look like? So this leads to a class of algorithms called value iteration, which basically does exactly this. This is just the Bellman operator with respect to the previous policies that we have. This previous policy, I'm just rewriting it, in its expectation form. And this policy was defined as the greedy with respect to my previous value function, which means that this expectation here just evaluates to the max of the previous value function. So by definition, this policy only selects the greedy action with respect to this estimate. So this whole expression evaluates to the max, which gives us a bit of a shortcut where we don't really have to represent the policy, the greedy policy anymore. We can just iterate this update in terms of the value function and converge to the optimal value function. Now, like, I kind of hand waved in terms of intuition, but this happens to be a valid update, and is called the Bellman optimality equation. And iterating this equation actually has the same properties as the previous operator, and is guaranteed to converge to the optimal value function. There are some details in there. It's just although I've hand waved how to get there, just to get the intuition that we're just trying to bypass the full extent of that computation. This, at least in the one-step version, gets us to an algorithm that actually we can prove that converges to the right thing and recovers the optimal value function. Okay, we're gonna, to finalize this, we're gonna look at a couple of instances of TD control following this principle. The first one is SARSA, which basically gets its name from this tuple, which is the current state, action, reward, associated, next state, and the action, which is the only thing that you need in order to update this value function. And let's go a bit through the algorithm. So we start the episode, and at each point in time, we select an action from a policy derived from our current estimate Q, which usually is an epsilon greedy policy. It has to be something improvement based, something like epsilon greedy or an epsilon softmax. Okay, we take the action in the environment, we obtain the reward and transition to the next state, and then choose the next action according to the same policy derived from Q, something like an epsilon greedy. And then we do exactly the TD update that we've seen before. This is the one-step target. And this is just the normal one-step TD update. Now, the thing to notice here is that usually for policy evaluation, we would keep the value, we would keep the policy fixed for a while, and try to back up in this value function the value of that policy. Now, this is doing this kind of shortcut. Where once we come back into this policy, you can see that the choice of the next action would be derived on the current estimate of the value function, which has been updated in the previous step. So this will change the policy as we migrate through the episode, as our value function updates, rather than keeping it still as a policy evaluation problem. This speeds up things quite considerably, and also, like tabular SARSA, so no functional approximator converges to the optimal value function if the policy is greedy in the limit of infinite exploration. So mild conditions, but you still have to get to all the states and actions, and this policy that we're deriving here has to be in the limit greedy. Okay. The other version of TD control that is based now on the optimality equation, the one that we've just saw, that instead of having the backup to the action taken, the sampled version, it's going to back up to potentially an action that it hasn't taken, but the one that maximizes the value function. The nice thing about this is that although in the book it says that we're still going to act according to a policy derived from Q, this is optional at this point. We can act according to a behavior policy as long as we have coverage of the state and action, and because we're not going to be backing up the value of the actions, or the action taken, we're always going to be backing up the value of the max of this value function. So we're going to do something in the environment, but we're going to learn a value function that does something, potentially does something else. So nice thing about this is that there's a disentangling between the behavior policy and the policy that we are trying to learn, which might be good or bad. Just to highlight the difference between basically these two algorithms is off policy versus on policy TD control. SARSA is an on policy TD control, where we are at each point in time trying to back up a policy that we're actually executing in the environment. The update is based on what we have done in the environment. The Q-learning, on the other hand, is an off-policy method where, like, we're going to use the experience that another policy has generated in order to update the policy of interest. And this is potentially very powerful because it allows for the reusage of the data. Reusage of previous data generation sources, like humans, other agent, or other policies. So this speeds up our learning and increases our potential sample complexity. Now, there are a couple of things that are different between these two methods. Not sure if I have time to go through this example, but let's try. If not, there is a very similar example in the collab, in the practical that you're going to do this afternoon, basically highlighting not only the differences between SARSA and Q-learning, but also more generally between on-policy and off-policy control. I guess the short version of this is that SARSA with epsilon greedy policy will recover something quite conservative because it always has the chance. So just to describe the scenario, this is just a normal grid, navigation left, right, up, down, and this portion here is a cliff that will give you a negative reward if you transition to that state. So this is the like large negative reward of -100, and every other step in the environment will give you a -1 negative reward. So evaluating a policy, an epsilon greedy policy, means that if you were very close to this edge, you have an epsilon probability chance of moving into the cliff, although you know what the right thing is to do. So a value function that backs up a policy like that will go for a safer route that is away from the cliff, that minimizes the probability of going through the cliff. At the same time, with the same experience, or potentially the same experience, Q-learning, although its epsilon greedy policy happens to perform much worse, can learn about the optimal policy, even with bad experience in a sense. This is because it always backs up the right thing to do, the optimal thing to do, rather than the thing that happened in the environment. SARSA will rely only on the experience that has happened in the environment, and this has a non-zero probability of going into the cliff and having experienced that negative reward. Okay, good. Okay, we can take another break now before moving to more advanced stuff, if there are any questions about control.
There are many questions, but I think we will be a bit short on time, so maybe let's just take a few questions and then...
how much time?
Like 5-7 minutes more. We can
okay.
So I'm just putting quickly the questions. So like the first question you've explained already, but if you could summarize again what the bootstrapping means in RL.
Is basically relying on your own prediction, your own value function, to form the target that you have in the RL update. It's updating a guess from a guess.
So given a set of RL agents, is there any way we can combine them or transfer knowledge between them?
Very good question. Yes, not necessarily very effectively. We can definitely, given the value function, we can transfer information in the value function and in evaluating their behavior. It depends how compatible the agents are, or if they share the same action space, state space, and so on and so forth. But like imitation learning and something like inverse reinforcement learning is looking at that problem, even if those constraints are not met, if the agents are not the same.
What are your views on neuroscience psychological view of RL? Should RL and DL in general merge together with neuroscience or diverge in their own way?
I think neuroscience at least has informed quite a bit our ways of approaching RL problems and the algorithms. I think vice versa too. There's a quite nice synergy between the fields. There are even like conferences like RLDM that look exactly at that, the confluence between RL and computational techniques, neuroscience, cognitive science, and so on. So very much a synergy between the fields that hopefully will continue to influence each other and improve each other.
When an environment can be defined to have sparse rewards?
Something like, let's say, Go, where the only feedback that you get is at the end whether or not you win or lose a game. You have no other signal. It's zero basically throughout the whole episode, and then you get it gets something at the end.
Even though more robust, why progress in research in RL is not as advanced probably as computer vision, NLP, or other neural networks based fields?
Because it's a much harder problem. And hopefully the next slides will highlight why this is such a hard problem.
Okay, so maybe let's go back to your slide because we are short on time. So please resume your presentation.
Okay, I have to do that again.
Yes, probably that would be great.
Right. Okay.
Okay, perfect.
Okay. Cool. You see? Yeah. Okay. Okay. So I have more planned for this segment, but we'll see how this goes. I want to highlight some of the challenges that makes this problem. If we don't think it's hard enough that we don't know the world, or all the interactions, or I think this is just a visualization, basically, of saying why this is what makes RL such a hard problem. First of all, we have a lot of states, many states. This is you know the curse of dimensionality from machine learning, but this is something on steroids at this point, because not only we have something like the explosion in dimensionality that we see in images, or high dimensional input space, but we also have this unfolding time, this time dimension that explodes our state space, especially when things are not in the observational space, are not Markovian, which means that we have the normal kind of input dimensionality that explodes exponentially, as most of the problem one. We have the sequential one that can be quite long-term sequences when we're reasoning about credit assignment and problems at consequences at this scale. And additionally, we have all of this unfolding, and all of this process unfolds in time dependent on the policy. So all of these tree and the possibilities and the probabilities of this the states that we're going to reach and the sequences that we're going to see in this environment are conditioned on the policy. The branching factor is conditioned on what we're going to do at this point in time. So we have these three dimensions where I guess most applications will have the first one. So vision will have something like the dimensionality in the image, which we inherit. The NLP and stuff like that will have still some of the sequence variability, like the time axis, but we have additionally this policy dependence, which policies in our space in the process of learning can be infinitely many. So these are many states. And just as a number, in Go, the number of these states and configurations are 10 to 170, and as a reference, there are 10 to 23 grains of sand on Earth, and 10 to the 80 atoms in the universe, which means that this number is, if every atom was a universe in itself, that many atoms, like it's more than that. So like anything that will try to not exploit a structure in that space and not put any constraints on the structure there is doomed to fail. There's no way we're going to tackle this. Like there's no way to store this. Yeah. And on top of that, again, the action space can be substantially large or even continuous. And even with these things, thanks to functional approximator, which is the main driver for our advances in the last 5 years or so, we still can tackle these problems under unknown environment and unknown conditions. And now a bit of a warning sign here that I guess has stagnated a bit the progress. Before 2013 is that we there are three, I guess, principles that help with the scaling up of these methods and tackling this kind of impossible task. One of them that I motivate is functional approximation. We need to do that. Bootstrapping, where we can't wait till the end of the episode to do this, and we have to reuse like intermediate solution to speed up the computation there. And off-policy learning, which is something that off-policy control like Q learning does, which helps us reuse data from previous policies or previous versions of ourselves. Unfortunately, when you do have these three conditions together, theory-wise, this happens to be a nightmare. In the second version of the book, Sutton and Bartow have identified this as potentially the deadly triad, where we can't control the bias of the solution that we're getting, and we can't even characterize the convergence or if this system converges to anything. Nevertheless, this is the scenario where all our methods or our state-of-the-art methods lie these days. So this is, this is the advert for more theory on this space, but it is really hard to say anything about this scenario. When eliminating some of these assumption, or like even if two of them are there and not the others, we can at least control some of these variables, some of these bias. But in general, we basically don't have any useful theory in this space, and this is the space that most of our advances have been in the past couple of years. And I think I only have time to just highlight a couple of the examples in functional approximator. The first one that I think it's worth mentioning, that deep learning has been applied, or well, shallow learning, because it was only the 2-layer perceptron at that point, was applied to RL and to the 2D learning back in '95 in learning trying to learn a gamma player. This was not common at that time, but it already showed the potential of a powerful functional approximator helping with this methods. Now, this was in '95. Deep learning winter later, in 2013, our colleague at DeepMind published DQN, which is now one of the most used algorithms in reinforcement learning, and this relies exactly on the same equation. It's still TD learning based on the equation. The only difference here is that we have better usage of the data. Because it's an off-line control method, we can reuse data from previous policies and have a large buffer of these interactions in order to update our value function. And the other thing that they introduced is usually in this target, in this TD target, we would always use just the previous estimate of our value function. This, when you have so many updates and so much data coming into play in these updates, this happens to be very unstable. So instead, they would be using basically a frozen network from previous steps in the past, and keep that network, keep the computation of this target based on the previous estimate fixed for a while in order to ground that problem and make it more stationary. Okay, and basically in terms of RL, the methods is the same. It's more about trying to make these methods play well with this more powerful functional approximator. And I think most of the work after that has been exactly the same, trying to make this work better and better with the functional approximator, with this functional approximator. And this is just a nice list of the things that have been done up to 2017, and you can see that most of them have to do with like a representation learning, richer targets for the neural networks to have better grounding. Prioritized replay is another way of servicing exactly this powerful function approximator. These other two can be applied in isolation, but it's all the learning method is the same. It's still Q-learning. It's just these are just ways of making this marriage between deep learning and reinforcement learning as efficient and as powerful as possible. And I think a lot of the work nowadays is in this regime. Okay, I think we're out of time, if I'm not mistaken.
Yes.
Okay. Yeah. The only other thing that I was planning on mentioning is the exploration problem, which I think it's oftenly overlooked, but in environments like in scalable environments, open world environments, even something like Go is a very prominent problem and a very complicated problem that we usually sweep under the rug. That to mention that all of the algorithms presented and stuff like that, convergence results, are in the conditioned on good exploration, the ability to actually see all states in action infinitely many times, which is by itself not a trivial problem. So this is more an advert to, if you want to start on doing research in reinforcement learning, this is a good area to go into. Cool.
Okay, great. Thank you. Thank you so much. I'm doing the clapping for everyone who's listening. So maybe let's just take 1-2 questions, because so that people can go to the posters after that. So one question is, what is the state of the art in RL?
Depends what state of the art means. I don't think we have like an algorithm that rules them all. Depending on the task, we have things that work very well on Atari. We have things that work very well on control task. They happen to be different things. There are also things that work particularly well on particular problems, like the exploration problem is actually a very pertinent example of this, that we just don't have an algorithm that works across the board. I think the one that works across the board more efficiently is something very trivial like epsilon greedy. And of course we can improve on that, but only for particular tasks. So it's unfortunately it's very task dependent.
Okay. For neural network, we need a large data set to train it. What kind of data do we need to start training an RL agent? Is it only state space, possible actions, and reward?
So there's not really a concept of data set in RL. It's always interaction with the environment. That's part of the exploration problem. The other thing is it depends on how you're going to do the credits assignment. If you have a like if you decide on something like TD with one-step update, you only need a state action reward and the next state kind of doubles. If not, you might need the partial trajectories if you want to do something like an n-step return there. It depends on how you're going to update this value function. If you want to go the Monte-Carlo rate, you just need like full episodes. So it depends on your update.
Yeah. What are your views on inverse reinforcement learning and the state of the art in deep IRL?
Okay. Not sure about the state of the art in deep reinforcement learning. I'm assuming because the principle is it turns out to be a reinforcement learning problem. Anyhow, it's just we derive the I guess the reward signal from the experience and from a demonstration. I would assume it has the same properties as the reinforcement learning problem, that it depends on the problem. I think it's a nice framework to deal with demonstration data, imitation data, and so on and so forth. I guess, more interested in the pure RL setting where we just don't know anything. The agent is dropped into the environment and it has to figure out things for itself. And it's more of a, like, I like to think about that problem because it biases less the solution rather than starting from something that humans do. Over and over again, we've seen that letting the agent learn from scratch can actually lead to substantially better solutions that we wouldn't have thought of. It's a question of whether or not we for the task of interest you can get any traction with pure RL.
Okay, so, and maybe let's start end with this one. To start learning RL, do you recommend studying theories and equations or implementing some ready codes and learn from them?
Definitely have the principles, like the kind of things that we've seen today, because I think a lot of people who start only at the code level, or there are a lot of agents out there and you just play with these agents, they don't even realize where these equations come from, why do they work, why would they converge to something, why does this loss make sense, and I think it's nice to have at least some of the fundamentals in there, and also to understand, especially when things go wrong, which of these assumptions are you violating, and to try to make your scenario or your algorithm more close to the things that we know in theory would work. For me, that's a very good way of debugging what's going on.
Okay, yeah, that makes a lot of sense. So thank you so much for giving this great talk on fundamentals. So I hope everybody managed to tune in. Okay, thank you so much. And everyone, please head to the next poster session. Okay, thank you. Bye.